With most power cycles, some form of theoretical thermodynamic cycle can be used to approximate the heat engine in question. The Carnot cycle, developed by Sadi Carnot in 1824, is a theoretical cycle that clearly illustrates the basic principles of thermodynamics and provides comparison for heat engine performance. To understand this power cycle, it is important to know some of the terms used to describe the dynamics of the cycle. Enthalpy is the term used to describe the thermal energy contained in the working fluid. Entropy describes the thermal energy in that same working fluid that produces no useful work output. This power cycle is comprised of 4 processes and assumes the working fluid is an ideal gas. From points 1 to 2, heat is added to the working fluid or gas at constant temperature from a heat source, resulting in expansion work and some change in enthalpy of the gas. The next step from points 2 to 3 provides for work output due to expansion of the working fluid, but with no heat transfer out of the fluid and no change in entropy. From 3 to 4 is a constant temperature heat rejection to the surroundings equivalent to the compression work performed on the working fluid in the next step and any change in enthalpy. Finally, from 4 back to 1 is constant entropy compression back to the starting temperature as work is performed on the fluid with an equivalent increase in enthalpy. The Carnot cycle is a completely reversible, closed cycle. For a power cycle to be completely reversible, the processes within the cycle do not experience friction, unrestrained expansion, mixing of different substances, transfer of heat across a finite temperature difference. Additionally, there must only be heat transfer from the high temperature source to the working fluid, and from the working fluid to the low temperature sink. Since in a real system it is not possible to achieve these conditions, the Carnot cycle is a theoretical cycle and is not attainable.